Now, you need to take notes, right? This is important. Traveling means going from anywhere to anywhere, right? That's traveling. The basic traveling that we do is walking or a walk. When I go out for a walk, I don't have a set pattern in my mind that I will go from here and I'll just stroll around, right? So I might go to a street multiple times. I might pass through a point multiple times. I don't care. So walk or walking means from anywhere to anywhere, repeat any number of edges, repeat any number of vertices. So for example, let's say you have a point A, let's say you've gone out in a park, you've got a point A, you've got a point B in the park, you've got a point C in the park, and let's say you've got a point D in the park, and you've got a point E in the park. Right? Now, I can walk from anywhere to anywhere, here, 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 here. I don't care. So when, and these are the edges, I can repeat any number of edges, any number of times, and I can pass through these points any number of times. So that is called walk. So if these are vertices, if these dots are vertices, and these joints are edges, so walk means repeat vertices and repeat edges any number of times. That is a walk. All good? Got my point? Now, I'll take this off the board, and then we will go to the next type of walk. So let's do a diagram here, that will make more sense. So let's say we've got this kind of structure. This is A, this is B, this is C, this is D, this is E, this is F, and that's G. Right. I'll take a different color as well. So that. Now, how many vertices do we have here? How many vertices do we have here? 1, 2, 3, 4, 5, 6, 7. 7 vertices. And how many edges do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Around 10 odd edges, right? Now, the second type of travel is called a trail. A trail is a walk. It is a kind of walk where you cannot repeat no edges. You cannot repeat edges, but you can repeat vertices. But you can repeat vertices. So for example, if I go to A to B, and then from B to F, so to E, E to F, F to here, then here, and let's say I finish here. So I started here, that was my start, and that's my end. So what have I done here? Have I repeated any edge? No. Once, 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 once. Have I repeated any vertices? Yes. I came to B twice. While I was going, I went via B and I finished at B. So this kind of a walk. So we are doing A, to B, B to E, E to F, F to C, and C to B again. So we repeated B twice. But we did not repeat the edges. You see AB, there's no AB here. BE, there's no BE here. EF, there's no EF here. FC, there's no FC here. And CB, there's no CB here. So this is called a trail. One very important point in trail that we need to really think about is that your start and your end points are different. They have to be. Your starting point was A, your end point is B. Now, if I make my starting and end point as same without repeating edges, but I can repeat the vertices. That means if I make my start and the end point same in a trail, I call that as a circuit. So then it becomes a circuit. So that means if I'm going from here, if I come here, I can't go back to A, right? Because I have to repeat the edge, which is not allowed. So let's try to follow something different. Let me just take another color. So if I were to go to a circuit, let's say I started here. And let's say I go to A, and then I go to C, then I go to F, then I go to G, then I go to D, then I come back here, and I finish here. Look at the green. Have I repeated any edge in the green? Anyone? No? A nod, yes or no, right? I need to see a nod, yes, no, right? Anything? Yeah? No, I haven't. But I have repeated the edge. So I have repeated the vertices. So what all vertices have I repeated? I repeated this. Right? So this is a cycle. So this is a circuit. So circuit means no edges. You can repeat the vertices and your starting and your end points should be the same. Have you seen those F1 circuits? Right? That's what the circuit's all about. They are not allowed to repeat the points, but the roads, but they have to go via different way. They can repeat the points, right? So that's the F1 circuit, right? That's the word. That's where the circuit word comes in. All good so far? Now let's do something called a path. Now when you cannot repeat an edge and you cannot repeat a vertex, that is a path. So no edges, no vertices. So if I were to make this quick diagram again, let's say A, B, C, D, E, F, and G, then my path will be, let's say A to D, and then probably D to C, and C to A here, here, and let's say here, and I basically finish here. So that's my start, that's my end. Another important point in path is your starting Your start and end have to be different. In this case, start and end are different. So what's the path? Path is A, B, C, F, E, and B. If you look at this one, you're not repeating any vertices, you're not repeating any edges. That becomes your path. And then the last one is called a cycle. Cycle is nothing but a closed path where you cannot repeat, so no edges, no vertices, start and the end have to be the same. Start, end have to be the same. Does it make sense? All of you? Nod your heads, please. Yes? Alright, cool. All good. Now, let's quickly draw a cycle. Let's see if I've got a different color. Yeah, I've got it. Yep. Let's draw a cycle. Very simple. I'm drawing it here. I start from, let's say, F. I go to E, I go to B, I go to C, I land back at F. Is it not a cycle? F, E, C, F. If I were to write it down, I will say edges, vertices, start and end. So walk. So for walk, you can repeat edges, you can repeat the vertices. And it doesn't really matter, start and end points are same or different, right? It doesn't really matter. If it's a trail, and I said repeat, you repeat, and so can you repeat the edges? No. Can you repeat the vertices? Yes. Start at the end point. What will happen? Have to be different. Then a circuit. You cannot repeat the edge. You can repeat the vertices. The start and the end point have to be the same. Then you've got a path. You cannot repeat the edge, you cannot repeat the vertices, start, the end point have to be different. And last but not the least, your cycle. You cannot repeat the edges, you cannot repeat the vertices, and they have to be the same. All good? The summarization? Yes? Now, let's go to the next topic, and I'll just take this off the board. Now what we're going to learn a bit more about this. We'll talk about Euler's trails and circuits. Euler's trails and circuits. So this trails and circuits here, they have another type, which is Euler's. Now, what is Euler? Was a mathematician who's just done a bit of work here. So the Euler trail basically, so in a trail, we are not repeating the edges, right? So a trail to be an Euler's trail, there are a few rules. So rules for the, I'll say ET, Euler's trail. Rules for Euler's trail. The first one is that the trail has to traverse or go through every edge of the graph. So it has to touch or traverse or travel through every edge of the graph. Number one. Number two, even if your trail is following every edge, that does not only suffice to be an Euler's trail. So then you need to look for the next rule, next set of rule. And the next set of rule is that your graph needs to be a connected graph for an Euler's trail to be present. What was connected graph? The graph where you can reach from one point to the other either directly or indirectly. That is called a connected graph. So if I have a graph like this, A, B, C, that is a connected graph. You can go from anywhere to anywhere. But then let's say if this was not there, then that's not a connected graph. You have an isolated vertex sitting here. So you cannot have an Euler's trail here. Right? So the first thing is, has to go through every edge. Second, it has to be a connected graph. Once these two rules are in, third and the most important rule is, it should have exactly 0 or 2 odd degree vertices. Zero or 2 should have odd degree vertices. What does that mean? Let's try to do that. Maybe A, B, C. How many? What's the degree here? Nanu, what's the degree of A? 2. Degree means how many edges are connected to a point. How many degree? What's the degree here? 2 again. What's the degree here? 2 again. How many odd degree vertices are here? 0. Right? So this falls under the category of Euler's trail. Yep. And let's say you've got something like this. Now, what's the degree here? 3. What's the degree here? It's still an Euler's trail because now you've got exactly 2 vertices that have odd. But then if I add here as well, now what's the degree here? What's the degree here? Still an Euler's trail? Why?
Still has 2 odd vertices.
Either of the two, either 0 or 2. I still have 2, no? Yes or no? So, if any of these 2 are present, it's a Euler's trail. then if this rule is in, then there are certain small rules underneath it, which says if there are no odd vertices, if you have 0 odd vertices, then the Euler's trail can start from any vertex. The Euler's trail can start from any vertex. But then if there are 2, then the Euler's trail has to start from the first odd vertex, odd start and odd finish. You cannot have a scenario in the Euler's trail which has 2 odd vertices where it can start from an even vertex and end anywhere. It has to start from an odd vertex, has to end at start on an odd vertex. Euler's circuit. What was circuit? A closed trail, right? That is what circuit was all about. Now the rules for circuit is, if you have an Euler's trail that starts and ends at the same point, simple, that is a circuit, right? But the rule is slightly different, wherein the Euler's trail has the 0 and 2 odd vertices. The Euler's circuit should have all vertices to be even degree. So here this degree 2, degree 2, degree 2, right? Is it an Euler's trail? 0 odd degree? Yes. Is it an Euler's circuit? So for Euler's circuit, all vertices needs to be even. Yes, it is Euler's circuit as well. It has a trail and it has a circuit. Now, and they can start and end. So if I say from A to B to C to A, that is a circuit. Yes, and it's a Euler's circuit as well, because the degree is 2. Got my point? Yeah. And if I would have said A to B to C, what would this have been, Tanu? Euler's trail. So it's a trail and it's an Euler's trail because it follows the 0 degree. The moment you're asked to find whether that's an Euler's circuit or a trail, Ethan, in that case, the first thing that you need to scan here is the degrees. Right? Yeah? If you find this, a trail. If you find this, an Euler's circuit. All good? Any dramas? This was very, very straightforward. All good? Yep. Let's do the question here that we were just doing, which was question, what was the question? Question 3, right? Let's do question 3. All good. So we had tracks and circuits as Euler's. Then we have paths and cycles as another wonderful guy called Hamilton. Sorry about the spelling. So let's understand what is a Hamilton path. PH path, the Hamilton path. Hamilton path is very simple. And the good point is that this guy hasn't confused us like Euler. So he hasn't given like formulas like even degrees and odd degrees. He's kept it very simple. He says any graph, any walk which touches all the vertices of your network is a Hamilton path. What is path? You don't repeat the edge, you don't repeat the vertex, but if you touch all the vertices without repeating them, it becomes a Hamilton path. So this is when you touch all vertices in a path, it becomes a Hamilton path. Right? And the last one is Hamilton cycle. And Hamilton cycle says, what is a cycle? Cycle is a path that starts the endpoints are same. What is Hamilton path? That goes to every vertex. So what is a cycle? A Hamilton path where your starting and the endpoints are same. So a Hamilton path, a H path, where your start and the endpoints are same. That is the Hamilton cycle. There is no formula for Hamilton paths and cycles, so it's just the visual inspection that you need to do. You need to really put your brain in it to find Hamilton paths and cycles. Right. I will stop here today. I've finished this chapter, the 11C now with you. And 11 or 13? It's 11, 13. So I've finished 13C with you today. And next week onwards, we will do the weighted network.